Alexander, would you like me to introduce you and start?
Maybe I should just say.
Sure, that would be nice. I'm basically just not really sure, like, how long to wait for people and at what points to cut off and be like, you have arrived late. Suffer by missing the first 3 slides.
Yeah, like it's 5 minutes past it. Like, no,
All right.
No.
Sweet. Need a couple more seconds.
As an academic, I have to introduce people. I don't know why. So Alexander will talk to us about the grand unified theory of reinforcement learning.
Decision estimation coefficients. Discovered by smart people who were not me. I had nothing to do with this, but I figured that people should know about it.
It's okay. It's well paced.
And now we begin. It is not generally known, but we do sort of have a general unified theory of reinforcement learning now, which is centered around a quality called the DEC, or decision estimation coefficient. If there's sort of a general unified theory about the limits of reinforcement learning, that seems pretty agent foundation-y, so I figured it was worth doing a presentation on this sort of stuff. What's notable here is that there's basically enough species of reinforcement learning problems to stock a zoo into half. We got multi-armed bandits, linear bandits, tabular MDP learning, a zillion and a half variants of MDPs where they go, yeah, the space of observations and actions is really big, but we're assuming some nice structure that makes it easy to learn. The list just goes on. And in all of these variants of reinforcement learning, a bunch of mathematicians have spent years of toil on improving the state of the art. There's a whole bunch of papers that are lurking on arXiv that are like, in this and such obscure variants of this and such reinforcement learning problem, we have a new and improved algorithm that shaves off a factor of square root of s from the state-of-the-art regret bound. And like, all 6 people who've read the paper clap, and yeah, and then the person who wrote it gets high status among like less people than fit in this room. It's great. My contention is that there is an alternate timeline out there somewhere where the decision estimation coefficient was discovered early on, and the various reinforcement learning problems got cleaned up with far fewer total mathematician years expended by just going deck go brrr. Timelines are short, so if our quests lead us to a reinforcement learning problem, we should be exploiting a general unified theory to spend math months on it instead of math years. The deck will not solve your problem for you, but it does have a very good tendency to focus your attention to the minimal set of insights that you need to have in order to solve it. So what is the deck even? The setting we'll be working in is as follows. On each round, you take an action. You observe an outcome and a reward, and repeat. Action, outcome, and reward, and you just sort of keep doing that. It's basically sort of a episodic setting. Hypotheses, or models, or whatever you want to call them, are functions from actions to distributions over outcomes and rewards. And your job is to get lots of reward. This is the setting that the deck is typically defined in. There are a bunch of variants of the decision estimation coefficient for a bunch of different things. For instance, we can add contexts. We can be like, before each problem, we see some starting information that tells us what sort of problem we're facing. Instead of just getting an outcome at the end, we see some context for what sort of problem we're even facing in the first place. And it's pretty trivial to adapt the deck to that setting. And there are variants where you do not see the rewards. The rewards are invisible. This is particularly useful for utility function learning. After all, different hypotheses about morality have to make different empirical predictions about human behavior and how humans would answer various questions, because otherwise morality doesn't connect to reality at all and is completely unlearnable. So we got to use the visible observations to infer the invisible rewards. Oh wait, hang on, then we sort of go back. I don't have time to get into all the variants for all the little different perturbations on the problem setting, so we're going to focus on the vanilla setting, which is basically just a multi-armed bandit problem. The space of actions can be as big as you want. The space of outcomes can be as big as you want. It's basically a multi-armed bandit problem, maybe with a zillion arms, and instead of the arm just giving you a reward, it also does some other stuff, maybe beep, maybe the arm turns colors, pull an arm, get an observation and a reward, repeat. Simple as. And the action and observation space, I said they can be big, but like for an episodic MDP setting, your action is a policy. Now, there are a lot of policies, and for your observation, it is an entire history for an episode. It is an entire trajectory. So, just because we're in what's basically a multi-armed bandit setting, we can accommodate very large action and observation spaces to still let us, tackle some MDP-like settings. Now, the fundamental obstacle to making good decisions that makes it harder than just predicting things is, even if you're really good at predicting things, you only can really guarantee good predictions about the consequences of actions you do. If you keep going right, you are quite accurate about what happens if you go right, but your predictions can be arbitrarily bad about what would happen if you go left, if you repeatedly don't go left. Predictions can be arbitrarily bad about the consequences of actions you don't do because you don't get feedback on them. However, there are a lot of things you could do, and you can only do one of them, so most of your predictions are bad because they're about what lies down an untaken road. That is what makes things hard. Another thing is that most regret analysis in reinforcement learning follows the following pattern. You try to set up a fork that's like, one of two things are going to happen. Either we are going to do really well and maybe not really learn much, or we are going to get our butt kicked, but we are going to be surprised by that and learn and acquire information and chop down our hypothesis space. We are good at learning. We cannot keep being surprised over and over. Eventually, we will catch on and narrow things down. So the second prong of the fork, where we lose but we at least learn from it, corrodes into nothingness over time, leaving just the prong where we do well but maybe don't learn that much from it. Keep this in mind. This is sort of a core unifying pattern that shows up over and over across reinforcement learning. You either do what, if you're not learning, then you should be at least doing well, and if you're losing, you should at least be learning from it. Now, if this would not be a proper agent foundations discussion if I didn't have omega involved in it. So, it's new combing time. We will be assuming two omniscient predictors here, omega and alpha. We will be assuming that you can randomize your action, but they will know how you randomize. They know your distribution over actions, not what you do. You got actions. You got beliefs, which are about how good the actions are. You got hypotheses that are also about how good the actions are. P is your distribution over actions. And your hypothesis space is, your batch of a zillion possible hypotheses plus your beliefs. Your beliefs do not necessarily have to be part of your hypothesis space, but we're going to be throwing them in anyways. Your job is to pick a probability distribution over actions that doesn't do too much worse than the best action. This is your expectation of how well you do. This is the best you could possibly do. And you are trying to minimize this regret gap between best you can do and what you actually do. However, there's a bit of a problem, which many approaches share, namely that you don't actually know the true hypothesis. So, not only do you not know the true hypothesis, it was picked by Alpha, who wants to see you screw up. So, now you are trying to minimize the worst case regret gap between the best you can do and how you actually do. However, hang on, alright, there we go. Fortunately, Omega descends from the heavens and says, by the way, for the probability distribution over actions that you will pick, the expected gap between your beliefs and what Alpha picked is small. Let's say blue is our beliefs and red is the reality that we don't know. So let's say you pick the best action according to your beliefs. You are like, I will pick right here. All right, cool. We're pretty accurate right here. But because we're not taking the other actions, we can be arbitrarily wrong about them. And we're like, oh hey, actually we're losing because a near mimic of my hypothesis, this is a near mimic because it's a near mimic on the parts you're actually checking, says that there's good reward over here. Alright, let's say we pick actions randomly. That means we do worse, but it also means there's less room to have a gap between your beliefs and true reality. So maybe there's a little bit of error everywhere, or maybe there's like a bit more error, but only on like an action with 1 in 3 chance. This is pretty much the form of the guarantee we get from being good at prediction. For the stuff we actually pick, or actually are likely to pick, the gap between our beliefs in blue and reality in red is small, but that gap can be pretty big about actions that we don't do. So you're trying to solve the following problem. We are trying to pick a distribution, P, that minimizes worst case regret. Regret is gap between best we can do and how we actually do, subject to the constraint that the expected difference between reality, M, and our model, N, is less than epsilon. The smallest regret versus true hypothesis that we can guarantee if we have a promise that our reality is close to our beliefs on the stuff we actually do.
You're kind of glossing over the Hillinger distance.
No, I'll get to that.
Okay, so.
So the expectation is taken, is sort of uniform over the ends in the hypothesis space?
Is that the hypothesis space is actually a max thing, but this expectation is over our actions.
So n is an unbound variable.
N is our beliefs. We are assumed to have a sort of like central belief in blue, and there are a bunch of other hypotheses, and we are just like, we don't know which true hypothesis is the real deal, but we do at least know that in expectation, according to what we actually do, it's pretty close to our beliefs.
So we're not assuming some kind of Bayesian updater thing where like this guy has one hypothesis and there's a bunch of other hypotheses they could have chosen, but they chose for these purposes they chose this one in particular this time.
You sort of have like a central hypothesis. You know, if you Bayes updated for a while, it's like your posterior after you've inhaled some observations. And there are what I'll call near mimics, things that are close to your beliefs on the actions you actually have a decent chance of doing. And you are basically trying to minimize worst case regret among the near mimics of your beliefs.
I see. Okay.
And this is a bit tricky because your distribution over actions changes what counts as a near mimic and also changes the regret gap at the same time. We could define this, the decision estimation coefficient, as this. It depends on epsilon, the strength of omega's promise. It depends on our beliefs, n, and it depends on our hypothesis space, h. This is not the actual definition of the deck, but it's intuitively really similar to this. The true definition is this. We'll break it down. First, instead of a hypothesis being a mapping from actions to rewards, now we got mapping from an action to distribution over outcomes and rewards. Let's say this R of M and A thing is the expected reward for hypothesis M and action A. So, if we got a model, we can do a thing and collapse our distribution over rewards down to an expected reward. So that's what this R of M of A thing is. This is pretty much the same thing. Minimum, worst case, regret, i.e. gap between best reward you can get and reward you actually expect to get. But the definition of low difference is weird. You're probably wondering what h squared is. That is the square of the Hellinger distance between the model M and your beliefs N. And also you square the epsilon for some reason.
That's actually pretty natural since you square the Hellinger distance. So you square
Yeah.
the
So this is pretty similar to the thing we had previously. We are minimizing our worst case regret gap subject to a promise that reality is close to our beliefs, except y squared Hellinger distance. I don't actually know. Also, we should check whether this passes basic sanity checks, and also the game with, yep.
Do you have a definition or some slide of Hellinger distance?
I will define it later.
Okay.
I will show you what Hellinger distance is. And the game with omega and alpha felt kind of arbitrary and not really motivated. And can we prove anything interesting about this
Wait,
one?
so the game with alpha and omega, I thought the motivation was because we have learned for some time, and supposedly our algorithm has some kind of learning guarantee.
Yes.
And so that's omega coming in and making the promise.
Yes.
And then alpha is but we.
Yeah,
don't know
we still
about
can't
things
split
that are
apart the
going
near
on.
mimics.
Right.
Yeah, alright. I guess that's motivation.
More basic question. Am I right in understanding that the way to minimize the policy that's going to the distribution P that's going to minimize the regret is going to be different to the distribution that's going to maximize the reward?
Yes, the distribution that minimizes the worst case regret under this promise.
Yeah, so because on the previous slide, it's like the thing you want to pick. Go on back one more, sorry. Yeah, the little cartoons. The leftmost cartoon, it's like maximizing your reward, but your regret's quite big. Is that right?
The leftmost cartoon is maximizing your reward with respect to your beliefs, but there is a near mimic where it turns out actually you are losing with respect to.
But you're still getting a lot of reward. Compared
Yeah,
to the other worlds where
you're
it
still
turns
getting
out
a
that
decent amount of reward.
more than in the other worlds, more than in the other options, even if they're missing
No,
out.
not actually. If this is true reality,
Yeah.
if you played this, you would win. because you are just picking the best according to your beliefs, and you are not exploring into here, you are losing and you don't even realize it.
Except that the counterfactual moves you to the next cartoon,
Right.
doesn't it?
Yeah, if you did take the rightmost action, then you wouldn't be in that world.
Only if we really believe
yes.
that alpha is like.
No, so this is like, if you're like, what is the possibilities? Like, is there a possibility where you're in a world where you're just losing out massively and you don't even know it? And if you didn't explore properly, that possibility exists, but it's not like you're changing reality by your actions. You're just like learning about it.
Yeah, so basically, the distribution over actions that does this thing is going to be one that is mostly doing pretty good, because if you're doing like horribly, then this regret gap will it tends to make this regret gap bigger, but you're still exploring enough into the other options to rule out stuff like
So
this.
is it unnatural to think of your belief as independent of the action of your actions? Because when you take actions, you're going to change your beliefs by learning things.
Yeah, we will get to that.
Okay, so,
So if, alright, I don't have a compelling narrative for why specifically we have to use Hellinger squared distance, but apparently it makes the math work real good. But anyways, on to what Hellinger distance even is.
Sorry, small question.
Alright, so if we work in
That's
Question
a-
is a small question.
yes.
So why the comparison between m and n is probability is a mean value, while you're minimizing in the worst case scenario? Couldn't you also have a worst case discrepancy between m and n?
So what we're sort of doing is we can split the space of hypotheses into two sets. The near mimics, those with low Hellinger square distance, and stuff that isn't a near mimic, which we would have like a decent chance of detecting, oh hey, our beliefs are wrong, or oh hey, this hypothesis is wrong. So if we can sort of split the space of beliefs into near mimics and not near mimics, then the deck is sort of about this piece that it's like, yeah, there are some near mimics that we are just not going to be surprised about, we're not going to gain information about. And there's all the other near mimics which we are ignoring, and maybe we lose because maybe it turns out they are actually right, but then we would learn.
All the other not.
Yes. All the other substantially different ones. So we're sort of splitting into two pieces, and we're going, either reality is going to be one of those near mimics, in which case we had better be doing well on it, or it is going to be one of, substantially different, in which case, oh hey, we find out we're wrong, or oh hey, we find out we're right, and we rule it out, or something.
Is the to make sure I understand? So my belief n, there aren't parameters in n that I'm learning as I go along.
N is updated over time at different time steps. N is different. It moves around.
Okay.
And what you're sort of doing is we're going, all right, splitting hypothesis space into the near mimics and everything else.
Yeah.
Either reality is going to be a near mimic of my beliefs, in which case, I'm getting low regret here.
Yeah.
Or reality is not going to be a near mimic, and I'm going to learn a meaningful chunk of new information, and I can't keep doing that forever. I can't keep being surprised forever. I will eventually catch on.
So n, I'm not learning in this setup here, right?
Mm-hmm.
This is decision for a single round.
So conditioned on, so there's a condition there. So conditioned on your being in a world that is a near mimic.
Yeah.
So like conditioned on you didn't learn anything.
Then we
you
want
better,
our regret
you
to
better
be
do
low.
well. And if you don't do well, and you didn't learn anything.
then it had better be something that is meaningfully distinct.
So to be clear, this is just some informal motivation for the definition of this mathematical object. There is going to be an actual algorithm how you use this mathematical object, and then there's going to be a theorem which says if you use this algorithm, then you get such and such guarantee, and conversely, this guarantee is closest to the alternative you can get.
Okay, thank you.
Yeah, so the square and Hellinger distance, like when the distributions are close, it becomes similar to the KL divergence.
Yes, a squared Hellinger is less than KL divergence, and I think the reason why we go with squared Hellinger over KL is, you know how KL throws a tantrum when like one distribution has epsilon probability on something and the other one has 0?
Right.
Yeah.
But if we're dealing with like rewards and 0, 1, throwing a tantrum about that doesn't really make a bunch of sense. And so Hellinger squared is kind of like KL, but it throws less of a tantrum in those low probability cases. So maybe that's why it's showing up.
Could you scroll back to the previous thing? So like this one here. So in this case, you're assuming that the payoffs are close. In the
Yes.
next one, you're assuming that the full distributions are close.
This
even
is the true definition that all the nice theorems exist about. This is the one that sort of intuitively introduces the same thing, except I don't have to explain what Hellinger squared distance is.
Okay. Thank you.
All right, on to what Hellinger distance even is. Working in the discrete case, a probability distribution has its entries sum up to 1, right? So, the square root of a probability distribution is something that has the sum of squares of its entries sum up to 1. So it is a point on the surface of the unit sphere. The Hellinger distance between two probability distributions is the L2 distance between their square roots.
Okay.
What?
Mm-hmm.
For some reason,
No,
taking...
how do you take a specific probability distribution and take the square root of it?
So if it's like 0.3, 0.4, 0.3, those sum up to 1. So you do like square root of 0.3, square root of 0.4, square root of 0.3.
But those do not sum up to 1, so then...
Oh no, but the sum of their squares is 1, so they are on the unit sphere.
They're on the positive.
Yes.
Alright, yep.
Yeah, so you take two probability distributions, you square root both of them, and you measure L2 distance, and that's Hellinger distance.
Cool. That's cute.
The square Hellinger. Okay. That makes
Yep.
squaring the Hellinger distance seems a lot more natural.
Yeah, so now for a sanity check. Let's say our beliefs are in blue, and there is an alternate hypothesis in red. And there are two spots of divergence. We have a bit of an exploratory one, where your beliefs and the alternative both say, it sucks a little bit, but there is a notable chance of getting to pry red and blue apart. They differ a little bit in the probability they assign to different observations. You got some chance of being able to tell red and blue apart if you go here. And then there's a really risky action where red says it's the best and blue says it is completely awful. What does the decision estimation coefficient tell us to do here? Well, if we just stay here at the default action, we can't rule out that true reality actually is the red hypothesis. And then there's a notable regret gap between how we're doing and the best we could do. But if we explore into the really risky action, that is a bad move, because we could get the same information with a cheaper test, namely repeatedly checking this thing that makes us only lose a little bit and has a non-trivial chance at splitting the two hypotheses apart. Note in particular, upper confidence bound approaches would mandate that you try out this risky action if you haven't done it yet, which is bad. The DEC says that the winning move is mostly picking this default action and randomizing a little bit over here. and the epsilon controls how much we explore.
And the reason that we don't, the reason that we don't always do the exploratory action is that it's a slightly lower payoff.
Yes.
And that's what you draw on, like the second red dot is a little bit below the first red dot.
Yep. Okay. Hang on.
So there's like, because if we have a low probability of taking, but low non-zero probability of taking the risk action, that might actually turn the red into not a near mimic, right? Because
Yeah, if we've got like a notable chance of taking this risky action, it does make red into not a near mimic, but it also means that we are like
because as long
losing pretty hard relative to best we could do.
yeah, well, I mean, if it's low probability,
Wait, why does your optimal action not depend on the relative probabilities you assign to red and blue? Oh, sorry, blue is your
Blue is your current beliefs. Red is the competitor.
Red is
So blue is an average over all the things that you think are true, weighted by all the
Yeah.
models you think could be true, weighted by the probability of them. Is that right?
Yeah.
and red is reality selected by an adversary.
Yeah, red is like a possible thing that you haven't ruled out yet because you've mostly been checking over here.
Why are we selecting by an adversary? Is it because we think there's really an adversary? Is it because we want to know the worst case?
It is because we are trying to prove bounds about worst case.
Cool. So just the prover is the adversary.
No,
Yep.
but the worst case is like over the hypothesis class. It's just standard uniform balance in learning theory.
Okay.
If hypothesis class, you want to prove that for every hypothesis there is like some.
We
reason.
converge to doing optimally to it. Yeah, so the DEC says the winning move is mostly picking this default action and with 5 epsilon squared probability, explore. In a certain sense, this is the minimal test that sacrifices the least utility, that renders the red hypothesis incompatible with Omega's promise that on average we're right. This is sort of like the cheapest possible test that sort of like splits red apart and makes it stop being a near mimic. But wait a minute, Omega isn't a thing, it didn't promise us anything. But note that if we do this over and over, in the absence of Omega, one of two things happens. Option 1, we find out our blue beliefs are right, and resume to just, playing it safe and winning. Option 2, our exploring finds out that red is right, and now actually we can go over here and rack up a whole bunch of utility. It's like the winning versus learning fork. We can only get surprised every so often, and then we settle into a nice routine of mostly doing the actual best thing, and we sort of do the minimal, cheapest exploration we need to in order to keep prying the remaining mimic hypotheses off of our back. That's sort of the key to it. Omega isn't actually showing up, isn't actually making any promises, but the deck basically recommends doing the cheapest exploration needed to pry near mimic hypotheses off of your mainline beliefs.
So what's interesting to me is it seems like there should be 2 parameters governing this decision: the difference between default and exploratory, and then the gap in the risky action outcome.
In the special case of multi-armed bandits, the deck optimal distribution over actions can be rephrased in those terms.
But there's only I guess there's 2 parameters, right? The 5 is presumably the 1 in 5 chance of distinguishable. And then, but the epsilon is taking care, it's somehow including both the cost of
Yes,
exploration.
the deck has sort of 3 parameters. One is your space of hypotheses that you are considering.
Yep.
One is your mainline beliefs. And one is your exploration versus exploitation parameter.
Right. I'm just thinking about the recommendation to go forward. Right.
So if epsilon is really small, that is mostly exploitation.
Right. And I guess what's surprising to me is just that you would think that the correct decision depends upon 2 things: how costly exploration is and how important it is to learn. But it only depends on one thing.
Yes, the how costly exploration is in this part, and the learning thing is in this part, which defines near mimic.
presumably it also depends on how devastating the risky action would be if it went badly, right? Because
Yep, for the really devastating ones, putting even a little probability on it makes the regret gap bigger.
How are we deciding what it is that omega is promising us? Because like we could just use the deck from the previous slide. What's stopping us from using that? Why do we have to use something fancy?
This is the one that all the really nice theorems are proved about, and if you go to other versions, you might be able to get a decent bound for specific problems, but they don't have super nice universal theorems attached to them.
Wait, are you gonna go into those?
Yes.
Cool.
On the next slide, next one. So the in the middle dot, the dots are only very little apart.
Mm-hmm.
So for purpose of explanation, those are like perfectly distinguishable, right? Is that what's going on? Or is it like they're harder to distinguish because they're close?
Let's assume that rewards are equal, but you know how there's like an auxiliary observation?
Okay, so I'm just wondering, when you're in this thing where you say there's no reason to go all the way in the risk action, is like the reason is that like if you take the middle action, you definitely
you have a 20% chance at like getting some special observation that splits red and blue apart.
Okay.
I don't remember seeing any part of the deck which took in observations.
The observations show up in the Hellinger squared thing. This M of A and N of A are distributions over this thing, and the observations, depending on the observations, that affects the Hellinger square distance.
Well, we're not.
The observations don't affect the regret gap. They affect what it counts as a near mimic.
Where are we weighing the differences in observations, though?
In the Hellinger square distance. If two distributions are very different in what outcomes they predict, their Hellinger squared is nearly 1.
But we're conditioning on that, right? Oh, but then
we are assuming that the adversary is restricted to picking things that are near mimics.
Maybe I'm just holding everyone up, but I don't understand why we would choose something which, like if they have the same reward, and they have the same worst case reward, why are we choosing the one with...
Because they may have the same reward at one action, but they may be very different in their predictions somewhere else, and if they are predicting different observations at the spot you are checking, then that is information you can use to meaningfully pry them apart.
I understand intuitively. I don't understand where it works in the deck map. Like, I feel like both of these options should have the same deck.
They have different sets of near mimics.
Okay, I just asked about this later.
So here are two hypotheses, M and N, right? They're identical, except with this weird wrinkle. And the reward is either 0 or 1.
Mm-hmm.
And the reward, and M, the reward is either 0.01 or 0.99.
That is why we have to use Hellinger squared, because that is an information theoretic notion of distance that would say that they are about one distance apart.
So in that case, those two
are very different in terms of Hellinger squared distance.
They're very different in terms of Hellinger squared distance, but in fact, for all decision making, they're practically identical.
Yes, for all decision making, they are practically identical they're practically identical for like that specific thing. But
it's interesting. I mean, it's counterintuitive, right? Because those are actually quite similar for everything we care about.
Yes.
They have a big Hellinger distance. Just a counterintuitive.
Well, I mean, like you can imagine a bandit problem where in like the low order bits, the low order bits of your reward in like the 20th decimal place are secretly encoding all the information about the bandit problem. Mm-hmm. And information theoretically, you can learn that quite easily by just pulling a couple arms and reading off the bit strings and looking at the really late ones. So the fact that we're using an information theory thing means that the deck does accurately capture that is information theoretically easy to win.
Oh, weird. So it's like, yeah, okay, so they're really far apart in step 1, but in step 2, wham, I know right away.
Yeah, they are very close in reward, but in Hellinger square distance, you can totally tell them apart, and you can totally read off a bunch of information from the low order bits, and the deck accurately captures that they are not near mimics.
Thank you.
All right. Now, another basic sanity check is actually the general framework of reinforcement learning theory kinda sucks. We don't really care that much about having high regret relative to the optimal player for a worst case hypothesis, because reality probably isn't worst case. If there are a bunch of hypotheses in the mountains that are really hard to tell apart, that makes our regret really high, but stuff in the lowlands of typical performance is easy to tell apart, the standard framework of RL regret bounds, since they are worst case, will say, for a worst case model, the regret is thus and such on mount upper bound. But really, we should be hunting for a result that's like, the agent realizes it is in the lowlands of typical performance and acts accordingly, getting regret way lower than our theoretical limit. If there is a reinforcement learning scenario that is general enough to capture reality in all its richness, it is also going to be general enough to encode super hard problem instances where we just sort of have to throw up our hands and go, you know what, I can't learn that. So any sufficiently good notion of learning to do well has to be the sort of notion that exploits it when it is in an easy part of the hypothesis space. And we would ideally like to not have to hard code that case analysis in, so if there's a subtle feature of a hypothesis that makes it easy to learn, that no mathematician has written a paper about yet, and our beliefs have that subtle feature, we should exploit it to get much lower regret in practice than in theory. The deck actually does that, which is why it has to depend on our beliefs, and can't be a belief invariant notion.
Wait, but the upper bound on regret they prove, it's still uniform though.
Yes, it's uniform over, like, worst case, but if, like, true reality may be something where in its vicinity, the deck is really low.
Do they really show that if you're in a hypothesis where the deck is locally low, then your regret is going to be low under the...
I don't think Foster showed that specifically, but it should be really, really easy to prove.
Okay, I'm not sure, but let's discuss it.
Yeah. So let's take multi-armed bandits as a simple example, because they are basically like the fruit fly or the roundworm of the reinforcement learning world. The thing that makes multi-armed bandit problems a lot easier in reality than in theory is the gap between the best arm and the second best arm. The really hard cases are the cases where all the arms look like roughly similar and you have to pull bad arms for quite a while before really getting to tell them apart. And the ones where you can get really low regret are ones where there is an obvious winning arm. And so, sure enough, if our beliefs say that a particular arm is clearly the best one, and you compute the deck in the vicinity of those, you will find the deck in that neighborhood is a lot smaller than its worst case value up on mount upper bound, and you will correctly recover the result that your regret won't have square roots in it, it'll have logarithms in it. Another quick note is that in some sense this solves the mystery of exploration. The deck tells you how much to explore. The papers introducing it repeatedly point out that various different mechanisms for exploration sometimes don't work. Hard-coded epsilon exploration? There's an environment where that loses. Thompson sampling? I didn't look super hard at their example, but apparently there's an environment where that loses. Basically anything with a hard-coded exploration parameter. They don't have results that are that general, but I am really suspicious about those now. In fact, actually, the first paper of the deck had a worse version because it had like a hard-coded ratio between how to value utility versus information. You had to like pick it in advance. And the successor paper introducing the version I presented here, basically went, here is a problem where in order to do the best, we have to adaptively ramp our trade-off between utility and information up and down. The old version loses because it can't do that, but the version I presented here adapts its exploration rate in the vicinity of whatever would be most convenient. All right, some water. And then, the results are pretty impressive. The deck is basically a hard limit on how well any algorithm can do. If you throw AIXI at a reinforcement learning problem, the deck sort of sets a limit on it. For these regret bounds, t is the number of rounds you're playing, and I'm going to be suppressing a whole bunch of constants and random logarithms and crap. But basically, for any decision-making algorithm at all that you throw at a reinforcement learning problem, there is a pair of hypotheses where on one of them, the algorithm will get about this much regret after t rounds. Remember, the deck had an epsilon parameter, so here we're taking epsilon to be like square root of 1 over t.
So here you should keep in mind that in most typical examples for small epsilon, the deck behaves linearly, and then this thing becomes just the square root over ground, which is what we're used to seeing.
Yeah, the reason square root of t shows up in a bunch of reinforcement learning bounds is because deck sub epsilon is usually in the vicinity of like epsilon. So if this is the hard limit, then you get like t times square root of 1 over t, and that's where the square root of t comes from. If deck sub epsilon scales as like faster than epsilon, you get really fast learning that's better than square root of t, and if it scales like sublinearly, you get regret that is like t to the 3/4 or something. But anyways, yeah, hard limit on how well you can do.
What's t one more time?
Number of time steps.
T is number of time steps. So if you play 1,000 rounds, t is 1,000. But the neat part is they specifically present an algorithm where if you give it a box that computes the deck minimizing distribution and a magic box that it for online estimation, which is basically predict real good, it'll have this much regret. Co of H is basically a technical detail about convex holes of the hypothesis space. The max shows up because, again, RL regret bounds suck and just tell you about the worst case. In the typical case, we do a lot better than this. And est is estimation complexity, which basically measures how good your magic predictor box predicts. A really bad magic predictor oracle has est being high. A really good one has est being low. So that's the hard limit.
So I think here it's important to know that this magic predictor box actually exists in many cases. Like for example, if your hypothesis class has finite
VC dimension.
Not VC dimension, much easier, just finite Minkowski-Boolean dimension. It's just anything that can be parameterized by finite number of parameters basically has this. Then you have a generic oracle that with estimation complexity just has this dimension in there. But
Predict well just means accumulate Bayesian evidence for.
You predict well means sum of Hellinger error grows sublinearly. So basically, sum of Hellinger error, if you throw like a Bayes optimal predictor at it, sum of Hellinger squared error will actually approach a constant.
Okay.
This constant is like the log h over delta thing that shows up all over learning.
Okay.
So est is something like log of the size of your hypothesis space.
So I guess I'm just asking practically, like for a particular decision problem, I can simulate the I can actually just do this. I can
Yes,
be a deck optimal person.
it would be, computationally intractable, but you could code up a brute force implementation of like approximately solve the deck, and you can code up a brute force implementation of throw Bayes' theorem at it, and you can just stick those two things in and go, I have an algorithm, even though it's really impractical, that gets this and such regret bound.
But in some cases you can also find a computationally tractable predictor and deck.
Like if I just had like a two-armed bandit.
Two-armed bandit. That is a case where solving this maximin problem is easy.
Yep.
So you can just code that thing up. It is really easy to do prediction. You just like average stuff together, and you just stick the two of them together and get something with optimal square root AT error.
The reason I'm asking is that, you could then, we could see how humans play these games, see if their decision making maps onto what the deck optimal decision making is.
Yep.
So I think for what they are bounded there, I think that even without before deck, the optimal play was already known.
Yeah, right.
Yeah.
So
And so it matches and so deck matches the optimal.
Yes. The deck has taken a bunch of results in RL theory and is like, it isn't the case that this is just like best existing bound. This has optimal asymptotics and nothing can do better than it.
I see. Thank you.
As it proves good lower bounds and good upper bounds. Now those deck terms, as I said, deck sub epsilon is usually on the order of epsilon. So you're usually gonna see like a square root of t showing up, and there's gonna be like a square root of estimation complexity thing.
Wait, so deck sub epsilon is usually on the order of epsilon. Sounds like deck is outputting a number.
Yes, it is a number.
Oh.
You can plug something in and be like, this has a value. This is a number.
So I think that
If it is-
this talk, it's just Alex loosely used it sometimes to talk about the number and sometimes talk about the probability distribution. That
Yeah,
achieves
see,
the
this
name.
is like, you're selecting a probability distribution. Not
Yeah.
a- What's
There
the
is the probability distribution that solves this
Oh,
minimax
right.
problem,
right,
but
okay.
also if the number is really small, you do good, you get low regret there, and if the number is really big, you do bad and you get high regret.
Okay.
Is it the square root whatever t is because of the way you set epsilon, like to
The
that thing you talked about?
the square root 1 over t is something that arises from the complicated proof they did.
But are you like you're chaining epsilon as you go?
Yes, as you go, epsilon shrinks, and you do a bunch of exploring at the start, and you go more exploity later.
Yeah.
So, if you go to the next slide, I don't know. Okay, so the lower regret bound, this one, yes, is that sort of like the learning? You can like how you like what towards the end. So you start out somewhere, you wander around the whole valley, and then like towards the end of your learning journey, when you're closing in, now you can say something about how quickly you get to the end. Is that a way of thinking about it?
Not really. I think I might have actually slightly botched this, but it is true that there are always a pair of models where on one of them it will have a regret that looks sort of like this.
Okay, and by pair models is that
You had
that they're at they're like within linear distance.
I would need to go back and double check the exact result.
Wait, what's the question again?
Because like so a pair, like if there's a pair of nearby.
Yes, because like you can always hard code an algorithm to be like do really well on this one exact problem, but then screw up on this adjacent problem.
No, the claim is that for any algorithm there will exist some hypothesis in your class where it will do badly.
Yes, but there's also the word nearby, and does nearby mean within?
I might have slightly botched this.
Okay, so Well, if you watch it, then what should it have said?
I think the true one is for any algorithm, there is a pair of hypotheses where one of them has regret greater than t times max sub n of this thing.
Okay, but the word nearby. So what's operationalization of nearby in the sense?
Okay, so you can like average together all the algorithm's decisions to get over the various rounds to get like a value of p, and then you can sort of take like this max problem to get a near mimic with approximately deck-sized regret gap that you have a decent chance of not having been able to tell apart.
Not really following, and I'm not really sure you're answering the question I'm asking.
And you're out of time.
Huh?
And you're out of time.
Yeah, okay.
Yeah. Wait, didn't I schedule like an hour?
Okay, sorry, there's another half an hour. We have,
Okay.
yeah, just if you need it.
Yeah. Time is just because we have sessions after.
Alright,
There's no
I
session
mean-
after.
And also because I insist on answering all the questions.
Well, yeah.
I am going to.
If we get bored, but
So I think the true claim is that if you define what they actually do in the paper, they take the maximum of the deck over all n inside a hypothesis.
Yeah, but you're answering a question about the
And then-
row 3, last row, and I'm asking to operationalize the word nearby in the middle of the sentence.
As I said, maybe it's because I like messed it up.
Forget about what's written here. I think
Alright.
the actual theorem that appears.
I can point you to the paper. We can see the exact
Alright.
precise thing. Alright. So,
also please post these slides.
alright, so
Please post
What-
these
what-
slides with appropriate
alright.
caveats.
alright, so what are the deck terms? Deck
That might be nice.
is usually on the order of like some problem specific constant times epsilon, and the problem specific constant is going to depend on things like number of actions and number of states and stuff. So usually you get like a square root of t, and and so in the usual case it turns into something like that, where c is a problem specific constant that like depends on number of actions and states and stuff. And so for multi-armed bandits, c is square root of number of arms. For tabular reinforcement learning, c is square root of number of states times number of arms times horizon.
And it's also important to know that estimation complexity is typically logarithmic in time. So it's definitely
Yeah. So yeah, it basically takes various bounds in reinforcement learning literature and is like, these bounds are optimal. Now, most reductions are usually of the form, we can solve this impossible problem if we could solve this other impossible problem. Usually if a problem calls an oracle, the hard part is getting shoved in the oracle. But this is an actual reduction of decision making to estimation. If you can efficiently solve the minimax problem, which usually you can't, although it gives you inspiration for how to sort of solve it, and you can go, here's a box that predicts real good. You can sort of paste the two together to solve decision making and get an algorithm that might not be optimal, because maybe you're like estimating inefficiently, but it does decently well. Mostly this just recovers a bunch of existing bounds in literature and does a bit worse than the best things mathematicians have found already. It hasn't found like a novel super algorithm, mostly just recovering a bunch of existing results and going, yeah, these are actually optimal.
Now, I think that some of the results are Foster's own, I mean, the weight gap thing, right? It's like came out of Foster's work on contextual bandits, where I think he did improve the state of the art, and then this thing matches it. So, I mean, yeah, you could do it without the deck, but it's kind of closely related.
So The deck is pretty handy to compress math years of effort into math months. It does not solve your reinforcement learning problem for you, but it does point you, but trying to actually prove a number for the deck points you directly at the core insights you need. You still have to have core insights, that's still kind of hard, but it's like inventing linear algebra with a cheat sheet of the form, here are questions that mathematicians were asking themselves just before they invented linear algebra. So, the process of trying to figure out what the deck even is at all, upper or lower bounds, forces you to have some good insights. The process of figuring out how to do something sort of like solving that minimax problem forces you to have core insights. Problem of figuring out how to predict real well, you gotta have some insights for that. You get pointed at all the insights you need with a minimum of dead ends, and you still have to do this, but this sort of takes like months and not years, and then you just paste it together and win.
Are there any examples where the deck of a bound is substantially worse than the rest of the bound?
There was a case where I used it in Vanessa's infraBayes setting to show that the existing t to the 2/3 bound actually could be improved to t to the 1/2, because I was like, here is proof that the deck is low.
No, I think the question was the opposite.
It was the other way around, yeah, it was the other way around. Is the deck of a...
I mean, notice that the lower bound and the upper bound are almost stuck.
almost...
They are almost stuck, right?
Right.
So the only difference between them is the estimator. So
Yeah.
as long as you have a good estimator, the deck cannot possibly be worse than anything else. So the only case where it can fail is if you have some example where you don't have a good estimator.
Yeah.
But that has to be something really wild, because like I said, even if you just have, as long as your hypothesis class is parameterizable by some
And you have
not too big number of parameters, then you have an estimator. So
Yeah,
it has to be
the
something-
estimation complexity is usually like log of number of hypotheses. And if you're more efficient about representing what counts as a
and how many examples
hypothesis.
where you don't have a finite number of parameters and still it works, like there's
Right.
non-parametric bandits. So to find an example where it doesn't work, it has to be something
Even more
very
crazy.
crazy.
Yeah.
So that online estimation oracle is basically an algorithm that takes histories and spits out belief. And we want the sum of the expected Hellinger squared distance between your beliefs and reality to be low. Ordinary, just throw Bayes' theorem at the thing, turns this into like log of number of hypotheses. If you throw some efficiently computable thing that is like information theoretically garbage, then maybe this thing is bigger and depends on t more. Basically, an online estimator is just an algorithm that looks at what you have done so far and outputs beliefs of the form, if we do this, this happens. You see some history, output some what-ifs for what's coming up next, continually revise it. It doesn't actually do anything. It's just along for the ride, just predicting. A good online estimator is something where no matter what agent it is riding along with, its beliefs about what will happen quickly converge to the reality of what will happen. The sum of its wrongness does not grow quickly. This is basically sum of the wrongness, and S is the upper bound on how quickly sum of wrongness grows. For good predictors, this bound is low. For bad predictors, it is high. If the agent stays in a dark room, a good predictor should learn the consequences of staying in a dark room with low cumulative mistakes. If the agent repeatedly buys a sandwich and randomly picks one of 5 sandwiches, a good predictor will rapidly learn the sandwich tastiness with low cumulative mistakes. If the tuna sandwich causes nausea, you should learn that quickly without making a whole bunch of cumulative mistakes. Estimation complexity for just use Bayes' Lamau is around, ln of number of hypotheses. The core assumption of the deck was that our beliefs were close to reality for whatever we actually do. So if the sum of our wrongness is finite, then the only way for that to happen is for our wrongness to tend to drop over time, eventually making the sort of foundational assumption of the deck true on a typical round. Now, I will take questions. Yes?
Hey, was M star the real world or like
Oh,
worst case?
M star is the real world.
Okay.
Now we will be taking questions, and I will be blatantly shilling the following up presentation, which is, let's say we're in Vanessa's infrabase setting, where hypotheses are more of the form reality will obey these constraints, then reality's probability distribution is thus and such. Turns out, the deck generalizes pretty well to the setting, although you gotta make a couple key modifications and have some new insights. But easily the biggest part is that atom-line estimation gets way more interesting than just use Bayes' theorem. There's deep connections to logical induction and Kelly betting and much more. And in particular, I'm going to be calling out like Scott and John and Daniel as people, and you as like people who would be really interested in attending that one.
When is it?
Oh, tomorrow, I think.
And
Oh, it's another like late at night one.
Okay.
I think it's the same time as this.
Yeah, so maybe this is like in the Mohawk talk, but like, so the deck assumes that there is a hypothesis that represents reality.
In
Yeah,
the
it's
classical
realizable.
case, yeah, there is a realizability assumption. In the infra case, there isn't,
I mean, in the infra
and we
case,
win
it's,
anyways.
You know, it's the infrared ability.
Right, which is still a realizability assumption, but a plausible one.
yeah.
Yeah, much weaker realizability.
Oh, I'm gonna be curious what that is. Impervializability? So
Yeah,
as
so
in your,
so-
your hypothesis space can reasonably constrain?
yeah, it's basically like if you're not trying to predict everything, but you're just trying to predict things like the probability of event A is less than 30%, then instead of speaking of the true hypothesis, we speak of a true hypothesis, which is just any constraint that reality obeys. Not necessarily trying to predict everything. So you can learn like 10 of those and paste them together to get a decent approximation of reality, and that sort of assumption isn't necessarily that we have an exact copy of reality in our hypothesis space, but just any constraint that reality obeys that is easy for us to learn, we are going to learn it and we are going to exploit it to do at least as well as it can guarantee.
So there is actually some work in the literature on non-realizable reinforcement learning. For example, with linear MDPs, there's some results where you have like some notion of how far reality is from your hypothesis class, and then you have a term in your regret that's linear. Like, you know, usually one agree to be sublinear. Here you have like some sublinear term plus a linear term, whereas the coefficient of the linear term is kind of some notion of how far reality is from your hypothesis class. So this kind of, there are some work. I don't know how to generalize the deck to this kind of thing, but this is also a thing.